All right, so some thoughts as we begin Module 2 here. We're going to be looking at the elementary derivative rules, which we'll be relying on for the rest of the class. So a couple things I want to cover today. The Leibniz notation and kind of why it's important. And then the derivative rules for constant functions, power functions, and exponential functions. So hopefully to go relatively quickly here. But a little bit on let's start with Leibniz notation. Okay, so we're used to, well, it's actually not Newton's notation, but the conventional notation. Actually, it's escaping me the name of the mathematician who this comes from, but y equals f of x, and then the derivative function y prime is f prime of x. This is the typical kind of functional notation for the derivative. And the Leibniz notation, so I don't want to have an arrow here. The Leibniz notation is for f prime of x, we use either dy dx or df dx. So it's kind of this ratio notation. And, you know, you can think about it as dy dx equals the limit as h goes to 0 of that f of x plus h minus f of x all over h. You can see how it preserves that ratio idea of the output over the input, output over the input. This infinitely small nudge in the input gives us this tiny nudge in the output. And we'll talk about, you know, what this dy really means a little bit later in the course. But when we say Leibniz notation, this is what we're talking about, dy dx or df dx. And it is equivalent to this f prime, but sometimes it just makes more sense to use dy dx. Okay, so if you see those two things, you can kind of pair them as meaning the same thing. Dy dx is not really a fraction, so to speak. It is the function f prime. So how to differentiate, excuse me, for constant functions. So find f prime of x when f of x equals 8. So let's use the original definition. So for f of x equals 8, what is f prime of x? Well, this is the limit as h goes to 0. F of x plus h minus f of x all over h, which is, well, f of x we know is 8, a constant. So f of x plus h is also going to be 8, right? So this is going to be the limit as h goes to 0. For any input, it outputs what? Just 8. So 8 minus f of x, which we said was 8, all over h, which is 0. Okay. So we see that this limit is 0, so the derivative is 0. So for f of x equals 8, this implies that f prime of x is the 0 constant function, which should make some sense if you think about it, that f of x equals 8 is the line, is the line y equals 8. And what's the slope, or the instantaneous rate of change of a flat line? Well, it's going to be 0. All right, the slope of the tangent line here is going to be 0. So that should make some sense. And, you know, maybe that's clear enough, but let's take again another look at df dx when f of x equals square root of 5. Well, again, f prime or df dx is the limit as h goes to 0 of f of x plus h minus f of x all over h. Again, this is a constant function, so it's really the limit as h goes to 0 of square root of 5 minus square root of 5 all over h, which is 0 again. So to generalize this rule, what we're seeing, and what we probably have already come to realize through our previous sections, is that the derivative of a constant function, our derivative of a constant function is going to be 0. So let's jot that down here with a little bit more space. So in general, for f of x equals, we can say k. We'd usually use this as a constant. For f of x equals k, f prime of x equals 0. So that is helpful to know. Okay, very helpful to know. There are often constants within functions, and when we differentiate them, we need to know that they're not changing. They're constant, so that their derivative is 0. All right. So at this point, too, we've played a lot with power functions. It's kind of the next simple level of functions to differentiate, which means to take their derivative. And what I'm saying here is at this point, we kind of know the deal. What's the deal with power functions? Well, we know that for f of x equals x squared, for f of x equals x squared, f prime of x is what? It's 2x. And for f of x equals x cubed, you can carry this through, and maybe we'll just do it real quick for the sake of illustration. We know that f prime of x is the limit as h goes to 0. Oops. We do know that this is cubed, though, so this is x plus h cubed minus x cubed over h. Lost my limit piece here. All right, when we multiply this out over here, this is kind of the most algebraically intense part of this. So we get x cubed plus 3x squared h plus 3xh squared plus h cubed. So that's all that first piece. Minus x cubed all over h. And again, I've lost my limit here. And so from here, some simplification should happen. This pattern continues. And so the x squareds cancel. And then we're left with the limit as h goes to 0 of 3x squared h. I'm actually just going to go ahead and pull this h out up top because I think you see it coming. 3x squared plus 3xh plus h squared all over h. And so these h's cancel. That's the only way you do that. And I've said that before. So now this is the limit as h goes to 0, and we've kind of simplified this problem greatly in that we know that this term's going to 0, this term's going to 0, and this term's going to 3x squared. It's staying put. So what did we just find? Well, starting with f of x is x cubed, we know that f prime of x is equal to 3x squared. So what is the deal with power functions? Well, we can generalize this. We can say for f of x equals x to the nth power. Well, we know that, x squared becomes 2x. If this is f and f prime. We know x cubed becomes 3x squared. So how about x to the 4th? Oh, that's not quite on screen there. So x to the 4th is going to be described by x cubed, specifically 4x cubed. Right, the power of the previous function times the function beneath it in the series, or in the sequence rather. So x to the 5th then is 5x to the 4th, x to the 100th power is 100x to the 99th, right, and so on. So this is a pretty important result. It's called the power rule. A lot of people learn it without understanding where it really comes from, which is the limit definition here. This will always hold up no matter how intense this expansion gets. And that's why this rule exists and works as well as it does. So in general, for f of x equals x to the n, so we don't have to create an infinite table to refer to, we say that f prime is equal to n times x to the n minus 1 power. Okay, and you can see how that holds up on these examples we made over here. This is called the power rule. Or you could call it the derivative rule for power functions, but that's why it's called that. So again, not to apply this indiscriminately, remembering why this is the case. And so if you need the derivative for a power function, this is how you find it. So I wanted to park for just a second and say that this should be a pretty crazy result. It seems so simple when you just look at it on its face, but for f of x, the cubic function, all right, let's remember what this looks like. It looks something like this. What we're saying is that 3x squared, the function 3x squared, which is a parabola, does this. That the height of this function at any point tells you the slope of this function. And that happens at every single point, right? Like the fact that that is the case should be somewhat mind-blowing. And this works for all power functions. And it's telling us that the power function previous to it in the sequence is describing the instantaneous rate of change of the one after it. So 2x, the line 2x is telling you what's happening at x squared, the slope at every single point. So it's kind of like there have been these speedometer functions that have been tethered to these power functions the whole time that we've never known about. And why that's super important is because a lot of times power functions are used to approximate really complicated functions in the real world. So for solving differential equations, things like this, we would drive something to power functions. So the fact that this is the case makes life so much easier. And this is why a lot of people think that, you know, they call it the unreasonable effectiveness of mathematics. It's like we don't have a good reason as to why these things are so, you know, simple and connected in this way. They just kind of appear as inescapable conclusions from the theorems we produce and the definitions that we've created and refined over time. All right, so that's just a little bit of nerding out to, again, point to what we're doing here. It's some deep stuff, even though you could look at this and be like, oh, this is a simple exponent rule, right? Or a simple little pattern we can use. So I'll leave you to practicing with that. And we'll move on to differentiating exponential functions. So this, again, should also be somewhat intuitive. I'm not going to spend a ton of time here. But what does an exponential function mean? Well, if we remember, you know, f of x equals ae to the kx for the continuous growth function. What this means is that this thing grows in proportion to the amount that you have, right? So the reason that populations grow quicker is because they're growing at a percent rate that is proportional to the amount that they have. So the more people that are in the population, the faster it's growing as at a flat rate. Same with, you know, interest in an account. If you have 7% interest earning on an account, the guy who has $1 million is earning that much more than the guy who has $1,000 in the account, right? So, but in definition, growing in proportion to the amount, that is actually telling us something about the derivative. If the derivative is the instantaneous rate of change, right, then what would we expect the derivative to look like? Well, we'd expect it to look like proportional to f of x, or like a scalar multiple of f of x. If it's going to grow in proportion to the amount, the derivative should have a similar shape to the function itself. And that turns out to be the case. So let's see. If we take a peek and I graphed 2 to the x, And I went ahead and graphed the derivative of 2 to the x in blue. And what we see is that it carries this shape of an exponential function. Let me pull my cursor over here. It carries the shape of an exponential function. But it's slightly slower than 2 to the x, right? It's not growing as fast. But I would say that it is proportional to it. It's like being scaled by something, maybe a value between 0 and 1, right? If you multiply something by like 0.8, you're getting close to the original amount, but slightly less. And so we see this relationship here. And now if I look at 3 to the x, kind of the next logical exponential function, I've graphed its derivative in red. And here you might see, all right, my original's in green, so that's 3 to the x. The derivative's in red. It also carries this shape of an exponential function. In some way, it's proportional to 3 to the x, but it's slightly faster than 3 to the x, right? So it's a little bit ahead of it, but still off by some, scale factor. So this is kind of interesting. All right, and I just also want to call special attention to this fact real quick, that for this function, the derivative was slightly slower, and for this one, it was slightly faster. So it might, beg the question, is there something in the middle? So the question is, what is that multiplier? What is that thing that when we go ahead and differentiate the function, that it seems to be scaled off by? Well, what happens is it becomes the natural log of a, and you'll work through an activity where you are, in essence, using the limit definition to come to this result by just needing one kind of special tool. But at any rate, it's, if you have a base a exponential function, the derivative is given by a to the x times the ln of that base. So for f of x equals 2 to the x, we know that f prime then is given by 2 to the x times ln of 2. And for let me use g here. For g of x equals 3 to the x, g prime is 3 to the x times ln of 3. And this carries for any general a. And what we see is, so if we go to approximation, ln of 2 is really around 0.69. So as I said, kind of a number that's smaller than 1, kind of scaling it down. And ln of 3 is 1.09, so it's kind of like multiplying by, 110%. And so this is what made this function a little bit faster than its original. So the question is, what about e to the x? So for e to the x, it still follows this pattern. It's base of a, so we've got f of x equals e to the x. The same rule applies. However, we get e to the x times ln of e. And we should remember from our log properties that the natural log of e, this is the power of e that gets you e, which is just 1. E to the x times 1. So we just say e to the x. So what does this really say? This might look confusing on its face. That for f of x equals e to the x, its derivative is itself. Okay, and this is one way in which the word natural, this is called the natural base with the natural logarithm, that the natural base shows how natural it is in that its height is equal to its slope at every single point. All right, so where you are on the curve for e to the x, this is another kind of mind popper here. Where you are on the curve e to the x, let's say you're at x equals 2. So you're at a height of e squared, which is, something close to 9. that means that that height, which is close to 9, is also the slope of the tangent line. So that slope here is e squared. And that is also the case for the second derivative and third derivative, things like this. So this is really kind of a very powerful result, and you'll always be happy to have e in your solutions because of how simple its derivative is. But again, it's describing this very natural change where the height of the curve is equal to the slope of the tangent line at every single point. Okay, so now this only works when it's this kind of what we call the vanilla flavor of e to the x. If there's scalar multiplication or other things within it, we need to use the appropriate rules. But this is an important starting step for this. All right, so just to kind of cover what recap what we've covered so far. We know that for f of x equals k, this implies that the derivative function is going to be 0 because it's constant. We know that for power functions, the derivative is described by the power function before it, n times x to the n minus 1. Oh, guys didn't see this up here probably. Okay, so constant functions have a 0 derivative. Power functions are described like that. And then for f of x equals a to the x, f prime is given by a to the x times ln of a. And I even want to put separately for e to the x, f prime is e to the x. So we've kind of covered 4 rules here. And so I wanted to talk a little bit about how we combine these rules and generalizing them. So when we have constant coefficients, this should be simple to deal with, and it is. Okay, so if we look at an example for 5x squared, if we carried this through the limit definition, I encourage you to do that relatively quickly. You can hit pause and do that. What you'll see is that we're left with 10x at the end. Okay, and so one way you could think about this is really 5 times x squared as your original function. You know that you're getting the derivative of x squared, which is 2x, and it's seemingly getting multiplied by this 5 at the end. And that is essentially the case. Since we're talking about the limit definition of the derivative, this scalar multiple in here of 5 can kind of be, factored out until the end, essentially, once we plug that in. So, get rid of this here. So, if I've got some g of x, which is a constant times a function, then the derivative of that function is just c times the derivative of the inner function. Okay, so exactly as we see it here. So in the same way, for just another example, if you've got f of x equals, let's say, 3 times 2 to the x, f prime is going to be, well, you can see that I've got this scalar times an exponential function. I know that this is a function that has a differentiation rule associated with it. It's got its own speedometer, and the scalar can be treated like this scalar here. So then this becomes 3 times, and then the derivative of that 2 to the x, which is 2 to the x times ln 2. All right, and then you can simplify from here by just combining the two scalars. But that's essentially what this rule means. So if you have a constant coefficient, it really doesn't, it just scales the same way. It doesn't need to be dealt with in any special way outside of that. And similarly, sums and differences. Through the limit of the difference quotient, these things are treated relatively nicely. So, if I have this function here, f of x equals x squared plus 5x, if I carry this through the limit definition of you know, x plus h squared plus 5x plus h minus x squared plus 5x all over h. If you carry this through, you'll see that this is equal to 2x plus 5. However, you could look at this and see, hey, this guy here, this 2x is the derivative of x squared, and this plus 5 is the derivative of a plus 5x, and that this actually also scales up. This is generalizable, that you could have done difference quotients for each of them. And so we see that, you know, for h of x equals f plus or minus g of x, this implies h prime is equal to the sum or difference of those derivatives. Okay, so this is again something that we can use now not just for power functions, but for polynomial functions or sums of power functions with exponential functions and things like that. So all sorts of different combinations come up from here. So let's not get quite there yet. So in general, though, one way to summarize this whole slide is for if I have some function h, which is, you know, let's call it a times f plus or minus b times g of x. A and b are scalars. Scalar coefficients, meaning not functions, just real numbers. And this tells us that h prime of x is a times f prime plus or minus b times g prime of x. Okay, and you'll have a chance to practice with that as well. All right, and lastly, I wanted to, you know, nod towards something that becomes a challenge, and it's dealing with products of functions. Okay, so it's not as simple as it might seem, and that's the tricky part, is that our brain kind of wants this to be as simple as it is with scalar multiplication and adding functions, but products of functions are actually different. So if you think about the function x to the fourth, we know that, and we want to know what its derivative is. We know that f prime is what? 4x to the third. Okay. But if we think about it instead of x squared times x squared, let's, you know, think about this for a second. And this is going to be incorrectly thinking about it. But if we think about g of x is x squared times x squared, and what does your brain want this to be for g prime? Your brain wants this to be 2x times 2x, right? Wants 2x times 2x. But that would be 4x squared, which obviously doesn't add up. So this doesn't work. And it's understandable. This is actually what Newton thought for a while. So the father of, one of the fathers of calculus, discoverers, inventors, whatever you want to call it, thought this was true for a bit until they proved it wrong. So the fact that you're nudging two functions at once and then multiplying that change together causes an issue. So one thing we can say about the products of functions is that it will require a special rule or some more attention. So it's not as simple as the derivatives of each. So what we can say is that it's not equal to f prime g prime. And I say that here again because I see this a lot when we're just kind of treating these things as shortcuts. So just to preface that. So the last bit here, I wanted to just go through an example using our rules so far and give you a pro tip. And that pro tip is that calculus is 99% algebra, and I've probably said that already at this point, but I'm going to keep saying it. And what I mean by algebra is rewriting expressions in helpful ways. So much of the time, the problem is about getting the problem to a solvable form more than it is about solving it, right? It's when we can get it to something that's workable, then we can come up with a solution relatively easily. So here, right, trying to do this as a product of two polynomial functions, two quadratics, would be, it wouldn't really line up with the rules that we have so far. We'll eventually get stuff to deal with things like this. But so what would be best would be to go ahead and expand this out. And so what we'll get is what, 3t to the fourth plus 3 of these minus 1 of those, so that's plus 2t squared minus 1. And so by first expanding, which isn't always what you're going to do, so you know, it's not always advantageous to do this, but here I saw that my rules don't quite apply, but if this thing were one big polynomial, which I'm used to this looking like after I expand them out, well, I've got rules to deal with that. So if this is p of t, now p prime of t is that much simpler, right? P prime is just a series of power rules. This guy is 3 times 4t to the third, and I can split over addition, so this guy becomes plus 2 times 2t to the first. And then this is a constant function, so that's really plus 0. The slope of that thing's 0. So this tells us that the derivative function is 12t cubed plus 4t. And wherever you have reasonable simplification like that, you should go ahead and take care of it. So don't leave this as 3 times 4, right? Condense those coefficients into 12, things like that. So the pro tip, this class is about a lot of algebra, and that's probably what makes it the most challenging. So to be on the lookout for that and to be practicing, and then and that rewriting is really key to solving these things. Getting them into a form where your rules actually do apply is typically the biggest challenge. All right, so I hope you found this helpful, and we'll see you in the next video.